In this video, we're going to talk about the basics of atoms. Some of this you might be familiar with from earlier classes. Some of it may be new to you, so we're just going to go over it. So let's talk about the subatomic particles. First of all, think about what sub means, like submarine, underwater. Subatomic means smaller than an atom. So those are things like protons, which are abbreviated with a P with a plus because they have a positive one charge. And they have a mass of 1 AMU. An AMU is an atomic mass unit, and that is a chemistry unit that is used, was made up to describe the mass of a proton. An electron is abbreviated with an E minus, the minus because it has a negative 1 charge, and it has a mass of about 0.0005 AMU. Now, I don't really need you to know the exact mass of an electron, but what I do need you to know is that in terms of its mass, it is much, much smaller than a proton. It's almost negligible when you consider the mass of an atom. The electrons are really tiny compared to the mass of the whole atom. With neutrons, neutrons are abbreviated N0 because they have no charge, they're neutral, and they have a mass of 1 AMU. And hopefully you guys can remember from back in your earlier science classes that protons and neutrons are in the nucleus and that electrons are around outside the nucleus. So you may have seen an atom represented this way. That probably looks familiar to you. Protons and neutrons in the middle, electrons around here on the outside on these little orbits. Unfortunately, that is not correct. It's very simplified, and when you were in middle school, it made sense to explain it to you that way, but an orbit is really too specific when we talk about where the electrons are. We now are going to learn about electrons being located in orbitals, which are not defined little circles like that. And so it's just like when your teacher taught you this, they weren't lying to you, but you really can't teach calculus to a baby. They don't have the mental capabilities, the academic capabilities to pick that up. It's the same way with trying to teach you what I'm going to teach you now. So the current electronic model is called the electron cloud model. And what it is you can see in the center that the nucleus is very tiny. You can see 10 to the negative 13th centimeters, very, very small. And then around the outside, you can see these different shaded areas. The more shaded it is, the more likely there is to be an electron there. The lighter and lighter and lighter it gets, the less likely there is to be an electron there. And then you can see that the size of a typical atom is about 10 to the negative 8 centimeters. So in comparison to the size of the atom, the nucleus is much smaller. So the nucleus is just really tiny and has all the protons and neutrons. It's very dense because we just talked about the fact that the mass of the proton and the mass of the neutron are 1 AMU. The mass of an electron is about 1/2000th of that. So most of the mass of the atom is in the nucleus. And then the rest of the atom is just empty space. And so there's empty space there, and the electrons just move around in that empty space. There aren't really specific orbits. You know, we think about the planets orbiting around the sun. They have a defined path. The electrons are just moving around in that empty space. So the cloud shows us the likelihood that we will find an electron in a given place. So again, where it's darker here closer to the nucleus, much more likely to find an electron than you are way out here. And when you think about the size of an electron the size of the nucleus versus an atom, think of the nucleus as a little green pea, and you've all probably had peas with dinner, and put it in the center of our football stadium. The edge of the atom would be out at the edges of the stadium. So the nucleus is really tiny in comparison, and those electrons can move great distances from that nucleus. Let's talk about how we describe atoms. You probably recognize this as a box from your periodic table. Every element has its own atomic number, and the atomic number is at the top of the block on the periodic table. And we call the atomic number Z, and it tells us how many protons an atom has. And so Once we know the number of protons something has, we know what it is. So gold always has 79 protons. Anything that has 79 protons, we always call gold, regardless of what changes, and we'll talk about some of those things that can change. It defines an element, the atomic number or number of protons. It's kind of like the DNA. It defines exactly what it is. Now, let's talk about the relationship between protons and electrons. Protons and electrons, when we have an atom that has no charge, if protons have a +1 charge and electrons have a -1 charge, and there's no charge on a neutral atom, then the number of electrons has to equal the number of protons. And it's a neutral atom, so pluses and minuses are equal. If an atom has a charge, it's called an ion, and that results from an imbalance between the protons and the electrons, and we'll get into that a little bit more later. If we have a positively charged ion, that's called a cation. And if you think about it, if you write the T, it almost looks like a plus, so cation is positive. And negatively charged ions are called anions, so A for A, N for negative, ions. So cations are positive like the T, and negative ions are a negative ion, anions. And then when we talk about an ion, it also changes the name. When we talk about iodine, that is the neutral atom. When we talk about the iodine ion, we call it iodide. That's how we recognize that it has a charge. And so when you hear about things like sodium chloride, chloride is an ion. Let's talk about how atoms do become charged. So it's that imbalance in the protons and the electrons. Now, we just talked about the fact that protons define what an element is, so they can't really change. The only way that the charge of an atom can change is that if the number of electrons changes. Protons are really down deep in the nucleus, and so it's really difficult for those to change. And so the electrons are out around in the cloud. It's much easier for them to change. When you have a positive charge, it means that you have more protons than electrons, and so that means you've lost electrons. If there's a negative charge, it means that you have more electrons than protons, so you've gained electrons. Remember that the protons cannot change. Okay? Here's a little comic relief for you. He's lost an electron. That means he has more protons. The red guy has more protons than electrons, so he's positive. All right. So let's talk about neutrons now. We've dealt with protons and electrons. Imagine 3 atoms. 1, 2, 3. So as you can see, they all have the same number of protons, the same number of electrons, but they have different numbers of neutrons. First of all, think about what element this is. Hopefully you recognize that with 6 protons, this is carbon. They're all the same element, but the atoms are different. And when that happens, we call the different elements isotopes. So those are atoms that have the same number of protons, but different numbers of neutrons. And you may recognize that isotope, that iso prefix, from the word from biology. Remember isotonic, hypertonic, hypotonic. Isotonic means that the concentrations are the same on both sides of the cell wall. Isotope means they have the same number of protons but different numbers of neutrons. So we have to have a way to distinguish between those. And so elements can have different isotopes of the same element. Just a reminder to recognize what an element is, we look at the number of protons, and carbon has 6 protons, so that means that it's carbon. So let's look at these a little more closely. So the mass number is equal to the protons plus the neutrons. So if we look at these different atoms, this atom has a mass number of 6 plus 6, so that would have a mass number of 12. Atom 2 has a mass number of 6 plus 7, so a mass number of 13. And then atom 3 has 6 protons and 8 neutrons, and if we add that, that would give us a mass number of 14. So those are different mass numbers. and that's how we can describe that. Now, one thing to be aware of is that not every isotope is represented evenly. So it's not like it's 1/3 atom 1, 1/3 atom 2, 1/3 atom 3. It is different amounts. It's just what's present in the atmosphere. And so we deal with that by using what's called an average atomic mass. And that's the mass that is on the periodic table, and we'll look at that in just a minute. So just remember that not every isotope is represented in the same amount. When we think about carbon-12, carbon-12 is kind of what we typically tend to see. Carbon-14 you may have heard of as used for radioactive dating, carbon dating when you hear about that. Pencil lead, which is graphite, it's made of carbon. It's a mixture of all of those. Let's look at the periodic table again. And we want to see how we adjust for those different isotopes. You can see that we use this average atomic mass. So this number at the bottom of the little block on the periodic table, that's the weighted average of the masses of all the different isotopes of that particular element. So for gold, there are some isotopes that have a mass number of 196. There are some that have a mass number of 197. There may be 195, 198, 199, but when you take that average atomic mass, that's the one that we use when we're looking at atomic masses of elements. And you'll hear it called just atomic mass most of the time. If you've ever calculated your grades by hand, so say in this class you know that tests are a certain percent, quizzes are a certain percent, homework's a certain percent. When you want to calculate your grade, you can figure out what your grade is based on the grades that you've earned, and you know that you count a quiz grade as 20%, a test grade as 50%, whatever percentage it is. And so it's like calculating it by hand. It's the same way if we look at the amounts. So with the atomic mass, if you look at carbon, carbon-12 is about 99% of the carbon on Earth. Carbon-13 is about 1%. Carbon-14 has a certain amount that tends to be in living things. So you just kind of maintain this very small constant amount of carbon-14 while you're living and eating. It goes into plants and animals. We eat plants and animals, so we constantly have this amount of carbon-14. But when you die, it starts to change. And by knowing how much is there, you can tell how long something has been dead. So let's look at how to calculate the average atomic mass. Just a quick example. Carbon has two naturally occurring isotopes. So carbon with a mass number of 12 is 98.93% of the carbon. And then carbon with a mass number of 13 is 1.07%. And this is the carbon kind of in the atmosphere. And then if you look at that, we're taking 12 AMU, which is the mass number, times 98.93 as a decimal, percent as a decimal. And then 13 AMU times 0.0107, so this percent as a decimal. And when you add those together, that gives us 12.0107. And if you look at your reference table, you'll see that you can find the atomic mass of carbon, and it's 12.01. All right, so there's some shorthand you need to know. There are symbols for this. The first thing is X, which is the symbol of the element, so that goes in the center. And then we use A as the mass number. That's a superscript. Remember, sub means below, super means above. So superscript is the mass number. So if, in this example, we're using carbon, and it has a mass number of 13. And then with Z is the atomic number. That's the subscript on the left-hand side. And Q then is the charge, so it's left off if there's no charge. In this example, we've got carbon, which has an atomic number of 6 and a mass number of 13, and no charge because there's not a number here. With the charge, there would be a number plus a sign. It has to be positive or negative. You have to give the charge. Sometimes you always see just the symbol with a dash and the mass number. So you might see it written as C-13. Or when we talk about like radioactive carbon dating, it's carbon C-14. So let's practice an example of how we figured these things out. So the first question I'd like you to answer from this, and look at the numbers, look at your periodic table, try to figure it out, pause the video. So answer the questions and then come back and we'll go through it together. So your first question is, what is the atomic number? Hopefully you remember that the atomic number is this number on the lower left corner. Okay, remember that's called Z. I don't know why it's not A, but it's Z. And so the atomic number is 22. What is the atomic mass? Now, I am willing to bet that many of you put 49, but when it asks for the atomic mass, it wants the average atomic mass, which is the one that is on your periodic table at the bottom. Don't forget to include the unit, AMU. When it asks for the mass number, this is the mass number. This is A, which is the mass number, so that is 49. Protons, remember that protons equal the atomic number, so you always know the protons if you know the atomic number. That's 22. And how many neutrons? Remember that protons plus neutrons equals the mass number. So if that's the case, neutrons, if we subtract protons from both sides, then those will cancel, and neutrons is equal to mass number minus protons. So that's 49 minus 22, which is 27. Now, when it asks about electrons, remember that if it's a neutral atom, so there's no charge here, the protons are equal to the neutrons. In this case, because there's a charge, there's an imbalance in the protons and electrons, and this one's a tough one. So if you know that it's positive, you know that it must have more protons. If it has more protons, we know that it has 4 more protons. So if it has 22 protons and it has 4 more protons than it does electrons, then we know that that would mean 18 electrons. Okay? So that we would take 22 protons and then subtract the charge. If you have questions about this, see me in class.